Welcome back to differential equations. In this video, I want to introduce you to special functions. Special functions are a very broad area of study in mathematics. They touch most disciplines in mathematics in one way or another. By and large, the functions that you've studied, the functions that we've worked with throughout this course and any previous mathematics courses you've taken, fall under the umbrella of elementary functions. Polynomials, rationals, radicals, exponential functions, logarithmic functions, and trigonometric functions, inverse trigonometric functions, and the hyperbolic functions, the hyperbolic sine, hyperbolic cosine, those sorts of things. And then any simple combination of a finite number of these is also considered to be an elementary function. Outside of that is the realm of the transcendental functions, the functions that are a little bit weird and a little bit different. Special functions fall under that umbrella. They are things that are not elementary functions, and the special in their name essentially means we found a reason that these are useful. There's a handful of them that are still talked about today. There are several that have been invented over the centuries with people who've been studying mathematics only to be forgotten, and there are new ones that come up relatively frequently in their own right. This course being a course in differential equations, we're going to focus on special functions that have some application to differential equations, usually in the form of a solution to a differential equation that we can't really solve analytically. And to that end, we're usually going to use power series methods as a way of expressing them. Let me get my head out of the way, and we will get started with this. Although I will start with a couple that are useful to know, but not really directly related to differential equations. The first one, which I mentioned because many of you may have come across at some point in the past, is the Gaussian normal curve. The Gaussian normal curve is a function of x, sure, but also of some parameters, which we usually write as mu and sigma. And it's calculated as 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared all over 2 sigma squared. You don't really need to know the particulars of this, but I think it's worth mentioning if you've not seen it before. This is the normal distribution that is fundamental in the study of statistics. Related to this, a very valuable function called the error function, which is sometimes denoted using a script e, or a little bit more frequently as ERF, all in cursive. My cursive Fs are terrible, but they kind of sort of mostly get the point across. Right. ERF of x is the integral, so let me get my coefficients correct, 2 over the square root of pi times the integral from 0 to x of e to the minus t squared dt. Notice here that if you take the Gaussian normal curve, you plug in mu equals 0 and sigma equals 1. I guess it's sigma equals 1 over the square root of 2. But plug that in and perform this integration, or plug that in and then integrate it, and you get the error function. The error function is kind of what its name suggests. It is a way of representing the error in a number of different sorts of calculations. Perhaps my favorite special function is the gamma function. Gamma of x is the integral from 0 to infinity of t to the x minus 1 times e to the minus t dt. And this is really only defined for x bigger than 0. For x equal to or less than 0, the gamma function has some issues. I'd love to spend an entire day just playing around with the gamma function. And if you had me for calculus, one of the things that I like to do on my spare days, if there's an extra day at the end of the course, is to dive into the properties of integrals to study some of the ideas of the gamma function, but I don't always have time for that, and I don't expect that you've seen that previously. The nice thing about the gamma function is that it is a way of generalizing the factorial. Some integer k factorial is the same thing as the gamma function evaluated at k plus 1. Right? For any whole number k. Right, so all of the properties that you're familiar with from the factorial still exist for the gamma function. For example, x times the gamma function of x is equal to the gamma function of x plus 1. That's perhaps my favorite of the properties of the gamma function. And that's something that we're actually going to use a little bit later in this video. All right, so the particulars of the gamma function are not that important. The particulars of the other functions are not that important, but I want you to be familiar with the name and the meanings. All right, let's get onward to actually talking about some differential equations. I'm going to mention two just in passing here. Hermite's equation is y double prime minus 2x y prime plus 2ny equals 0 for any integer n. The solutions to Hermite's equation are called the Hermite polynomials. And are generally denoted h sub n of x. We also have Legendre's equation, and the solution to Legendre's equation are called Legendre polynomials. And generally denoted as p sub n of x. Again, right, any integer n plugged in there will give you a different Legendre polynomial. I will be honest, I've never come across an application of Hermite polynomials, although I'm sure that there are plenty just outside of my particular experience. The Legendre polynomials tend to come up a lot more in places that I've been. Whether that's useful to you or not, I have no idea. But in the study of classical mechanics, I saw a lot of Legendre polynomials. So that's something that is of particular interest to me. For anyone who is or will be in the near future taking a course in linear algebra, the Legendre polynomials are very interesting because they are a set of orthogonal functions. We talked a little bit about orthogonal functions when we talked about the basic theory of second order differential equations, but not a lot. And again, I'm saving any further discussion of that for anyone who gets to follow up with a course in linear algebra. Right. For our purposes right now, again, I just want you to know that these are things. As you are looking at solving differential equations that may come up in the future, as you're reading literature on them, as you're asking for computer help in solving differential equations, you may find that you end up with, oh, the solution there is a Hermite polynomial, oh, or the solution there is a Legendre polynomial. And so you have some idea of what those names mean and what you can do with them. The big name that I want to look at in today's video are Bessel functions, which are solutions to Bessel's differential equation, and the mechanisms we need to solve Bessel's equation are interesting enough in their own right that I want to spend some time thinking about it. We've been looking at using power series methods to solve an equation in the form y double prime plus p of x times y prime plus q of x times y equals 0 using a power series representation of the solution. One of the things that we have to rely on in that is p of x and q of x have to be nicely behaved. In the video on power series solutions, I think I said it's best if they are polynomials. If they aren't polynomials, well then sometimes some weird things can happen that we'll talk about later. Welcome to later. The important thing, the technically correct thing, is that p of x and q of x have to be analytic at 0. Analytic is one of those words that gets thrown around and everyone forgets what that means. An analytic function is differentiable infinitely. All of its derivatives exist, all of its derivatives are continuous. And I do also want to point out here, I say must be analytic at 0, but it turns out that actually anywhere works. If a function is analytic at 0, then we can use a power series centered at 0. If we are looking at, for some reason, centering our solution at a different point, then we care about whether that point is analytic or not. But 0 tends to be the most useful one, so that's what I'm going with here. If it is the case that these two functions are analytic, we call it an ordinary point. And we are kind of happy, we don't worry about it. If it's not an ordinary point, then we say it is a singular point, or a singularity. And the reason for that is the same reason that we call a black hole a singularity. It is usually caused by a divide by zero error in the work you've done. Most of the time, when you're looking at a second order differential equation, there is some coefficient here that is not 1. And you have to divide by it on both sides of the equation to get the equation into this form. If the thing you're dividing by happens to be 0 when x is equal to 0, you divided by 0, you've created a singularity, we have a singular point. Now, when we have a singular point, we still might have a lifeline. If it turns out that x times p of x and x squared times q of x are analytic, we have a regular singular point. And for a regular singular point, we have hope. If that's still not the case, then you have an irregular singular point, and you need to find a completely different approach to solving the equation. When we have a regular singular point, we are going to use the method of Frobenius. Frobenius has a theorem, named Frobenius' theorem, that says that when you have a regular singular point, then there is at least one constant r so that the function y of x is the sum, k goes from 0 to infinity, of some coefficient ak times x to the k plus r. So there is at least one value of r, there might be more, so that you can find a solution in this form. X to the k plus r instead of just x to the k. The method of Frobenius tells us to take this solution, plug it into the differential equation, play around with it, see if we can figure out the value of r that gives us that solution, and then use that to find our recurrence relation the same way we did dealing with the power series solutions before. All right. Finally, we get to Bessel's equation. All right. Bessel's equation has a parameter in it. For reasons that are beyond my understanding, that parameter usually takes the form of the Greek letter nu, which mostly looks like the letter v. But we have x squared times y double prime plus x times y prime plus x squared minus nu squared y is equal to 0. And so we immediately see, oh, if I divide by x squared, I'm going to have problems because I divided by x squared. But luckily, I've already got a factor of x here. So if I multiply x over x squared times x, I'll get 1, which is fine. And then if I take x squared minus nu squared over x squared and multiply by x squared, I'll get x squared minus nu squared, which is also fine. So we have a regular singular point here. We can use the method of Frobenius, which almost is still on the screen. Right? We're going to have that y is the sum, k goes from 0 to infinity, of ak x to the k plus r. We're going to have y prime is the sum k goes from 0 to infinity of ak times k plus r times x to the k plus r minus 1. And then we're going to have y double prime is the sum k goes from 0 to infinity of ak times k plus r times k plus r minus 1 times x to the k plus r minus 2. And once again, I'm going to thank these coefficients for meaning that I don't really have to do the jumping through hoops that I've had to previously to get those into the equation. Because when I multiply y double prime times x squared, it will add 2 to my coefficient, making the minus 2 go away. When I multiply x times y prime, it will add 1 to this coefficient, making the minus 1 go away. And we very conveniently have the sum ak times k plus r times k plus r minus 1 times x to the k plus r plus the sum ak times k plus r times x to the k plus r plus x squared minus nu squared times the sum ak x to the k plus r. Right. So really the only issue we have is the x squared that's sitting right here. All right, let's see if we can do something with that. Well, I guess one way to think about that is to split this up. All right, so the first two summations stay the same. I am going to put my indices back on there. I'm going to stop being lazy. But then when I multiply, I just realized that I wrote a plus where there should have been a minus here. But then when I multiply out, x squared times the summation would give me x to the k plus r plus 2. And I don't want to deal with that plus 2. So I'll just start at 2 and subtract 2 from the index of my coefficient. The advantage of doing this is I can split out all of these things. I can look at the case of k equals 0 across the terms where it's there. I can look at the case where k equals 1 across the terms that it's there. And then, of course, beyond that, I will have what will hopefully give us a recurrence relationship. Right. So we will split out the k equals 0 terms. We will split out the k equals 1 terms, and then we'll keep our summation for k goes from 2 to infinity, and bring everything together in the same summation. Nope, that's all. All right, that's all the further I can get. So let's see if we can simplify this a little bit. All right, so just factoring out the common factors. And then if we clean up a little bit further, right, distribute, combine some like terms, I'm not going to write out all the details, but it's just doing some algebra to clean up each of these terms. And at this point, we actually get some arbitrary decisions to make. Using the property of polynomials that say that two polynomials can only be equal if their coefficients are equal, right? The same thing we used for the recursion relationship previously. Let's box the whole thing. Either the coefficients on all of these have to be 0. So a naught times r squared minus nu squared has to be 0. a1 times r squared plus 2r plus 1 minus nu squared has to be 0, and ak times k plus nu squared minus, ak times k plus r squared minus nu squared equals 0. You think that that was just my bad handwriting getting in the way, but no, that was actually me getting ahead of myself. All right. So remember from the beginning, I said the method of Frobenius promised us at least one value of r that would satisfy things. Well, we've got r is positive or negative nu, satisfies that first equation, and we might be able to get another solution out of that second equation, but let's just pick a1 equals 0 and then we don't have to worry about it. Makes our lives a little bit easier. And here, right, if I pick r is positive nu, then my equation here I can rewrite as ak times k plus nu squared minus nu squared equals. I got so excited about my jumping the gun that I forgot to write the rest of that equation out. Because there's still supposed to be a plus ak minus 2 in there, which has to also still be here. Right, now if I multiply that out, right, k plus nu squared is k squared plus 2k nu plus nu squared, and then we minus nu squared. So we've got ak times k squared plus 2k nu plus a k minus 2 equals 0, or a k minus 2, no, ak is equal to the negative of a k minus 2 over k times k plus 2 nu. And so from here, the only thing we have left to worry about is this a naught. And we could pick any value of a naught we would like as our starting point and be able to go from there. The usual way of dealing with this in the Bessel function is to make the obvious choice. I don't know who thinks that this is obvious, but they tell me it's the obvious choice, and I'm required to believe them because I am a math teacher or something. But we're going to pick that a naught is equal to 1 over 2 squared. Well, that seems a little bit weird in the first place. Times the gamma function of 1 plus nu. The gamma function. Okay. But no, that actually does make some sense. Because we've got this k plus 2 nu going on down here in our ak. And remember, the nice thing about the gamma function is if you multiply 1 plus nu times the gamma function of 1 plus nu, you get the gamma function of 1 plus nu plus 1, which is 2 plus nu. So if you do this k times, right, if you multiply the gamma function of 2 plus nu times 2 plus nu, you'll get the gamma function of 3 plus nu, gamma function of 4 plus nu. Eventually, you'll get the gamma function of k plus nu. So that's the reason that we're going through and starting there. But the general way that we write this out is we're going to put this as a to the 2n. Right? I'm switching from k's to n's because I specifically want to call out that we're only going to get even values here. But we'll end up with -1 to the n power. We'll get 2 to the 2n plus nu power. We'll get an n factorial, and we'll get the gamma function of 1 plus nu plus n. And then a 2k plus 1 is equal to 0. I glossed over a lot of things at the end there, just to give you some ideas on the notation. Everything from where I introduced my value of a naught here downward, that's just for historical context so that you know what's going on. If you're able to get that recursion relationship and this relationship, which I just realized I never wrote the name down for, this is called the indicial relationship or the index relationship, figuring out what R is in terms of the parameters in the equation. All right. It's tiring, it's messy, but it's not as bad as it seems. Here's something for you to take a look at. I've got here x times y double prime plus y is equal to 0. This is a much easier equation to work with than the Bessel function that I just showed you, but it is still a second order differential equation with non-constant coefficients. And because that x is on the y double prime term, if you try to divide it out, it will give you a singular point, which is thankfully a regular singular point, so you can use the method of Frobenius to solve this one. Take a few minutes to see where you can get to with that. Again, don't worry about actually solving the recurrence relationship and finding anything out with that. I want you to get far enough to derive the indicial relationship and derive the recurrence relationship, and if you can get there, I'm going to call it a fantastic job. See what you can do with that, and I'll see you in the next video.